Not doing,
It's not a gem.
no, I know. No, we won't. Is that just because you haven't printed them up?
Yeah, I was like trying to decide when I should be late or print notes.
Yeah. I stopped doing skeleton notes in the hope that now we won't have to write anything down and we can move faster, and or if I don't get there, it's already there for you, right? Okay. Might be worth reviewing for the homework, okay? So where are we at? We are at boundary conditions and implementing those boundary conditions. And how do we implement those on our nodes? What we talked about, right? This idea that when you fix something, you are giving it infinite stiffness, right? And that might not be your desired intent, right? It might alter the stiffness of the model in such a way that you're not going to be matching your mathematical model. And so VA allows you to do some things with respect to spring supports, right? With respect to displacements or rotations. We can make things one way or two way. We talked about those interactions, probably a little too much on Monday, okay? When we get to member elements, it's similar to nodes, where we can restrain the degrees of freedom for the member. And in this case, it's always in the local coordinates. Right, so in VA, this is the releases that you can apply. So I'm sure it's similar in reason. So,
Yeah.
right, so you're looking at the local degrees of freedom. You're doing that because it's looking at it with respect to the local stiffness matrix, right? It's going to start at that local level. So we're going to release this member at the local level, so then it can go through, right, and can calculate that K equivalent that we talked about. And so you just need to make sure you pay attention to local coordinates, right? In the homework, okay? When you look at the model, in the model view, there's a big, on the project manager side, we briefly went over it, okay, when I was going over VA. But there's a lot of things you can show and not show in the model, right? You can show member releases, you can show fixity at your nodes, you can show material type, you can show the section of your beams. You don't have to go through and click every single element in your model, right, to verify that it's the right size member, right? You can click on it and it'll show you all of that in that three-dimensional view, right, the ISO. And so it's very helpful to look at that. In this case, showing the local coordinates for the member is very important, right? Because the local y-axis might not align with the direction you assume, right, or the global y-axis. And so it's important to know which direction these are in. Also important here is they have the 1s and 2s denoted. Well, that's denoted based on where the coordinate starts and stops along the member length, right? So you might be releasing the wrong side of the member based on the fact that the coordinates, local coordinates, go the opposite direction than what you thought they did. Okay? And they go in the direction you draw the member. Okay? I also mentioned like this was one issue to look at with respect to our like shear and moment diagrams. If you pick multiple beams that are, say, along the line of, say, on the east side or the west side of the tower, right? There's members, multiple members that line the whole length. Well, if you picked all of those members and had it show you the shear and moment diagram for some load combination, right? If the local coordinates opposed each other, then you get these huge jumps in the moment diagram, right? It wouldn't be this nice continuous thing. It would have to be all the members in the same local coordinate direction. Otherwise, you'll get weird stuff going on. So we remember the derivation here. Is that when they calculate stiffness, they do it at the local level, and they are calculating, VA is calculating this K equivalent, and then they will assemble. So that's why releases are always based on the local level,
So,
because it's following the same workflow.
can you model a cantilever beam by making one side, having one side fixed, like, make axial, I guess you couldn't. I'm like-
You
I keep
you
thinking
could, I guess, Elias.
by making axial shear and moment, like, all rigid on, right?
You would have to release all degrees of freedom at the end.
On one end.
Yeah, which I've never tried that.
I was just like, keep.
I wonder
getting
if
in my head
VA
about
would
this, like, in
let
class we
you-
were saying you could either make your boundary conditions on the nodes or through the members, and you can achieve the same behavior with releasing either the member or the.
I'm not sure that NVA would allow you to release every degree of freedom, because then it's going to be like the element doesn't have a node out there, I guess. I guess you could fix it. You could fix that outside node and then release all of these if it allowed you to release them. I've never tried doing that, because that doesn't seem like the right
Yeah,
way to do it. But an interesting way to think about it, like you're thinking how,
Like,
you're thinking about the interconnection between the element and the fact that it has a node out there,
Yeah.
right? And this allows us to essentially release it from the node. And that's where I'm curious. I've never tried releasing everything, because that doesn't make much sense to do. It's like, why not just
right, just,
not have, or have the node there and
But
just
not
not,
fix it.
yeah, not fix the node. So it might have some things where it won't allow you to release everything on the end, but I've
like,
never tried
these-
it.
You use these when you have, pretty much, like, the only reason I'm thinking of, like, releasing some of these is when you have different like, one node that has different members coming in with different connection types.
Yeah, I mean, I would
You can't
say,
just have the node.
yeah, I mean, you
Right.
could have it, you could have a single member, right? And you do it with, if you wanted in VA to model a simply supported beam with a
Yeah.
uniform load, right? You need to put pins at the end,
Right.
right? So you could either fix the nodes and then release the moment, right?
At the node.
At the node to give you that pin, or you could not release the member and then put the boundary condition on the node itself, right? So then the node no longer becomes fixed in all degrees of freedom, it becomes the pin, right? It can rotate. But then the member is fixed to that node.
Right, and usually you wanna go with the nodes, like.
Correct, if you can, yep.
But this is used just when you have different boundary conditions all coming into one node, basically.
Yes, I would say so. I'd say predominantly
That's the purpose of
based on,
this,
yes,
right?
to allow you to, like if you had like the columns that's sitting out here and you have multiple beams framing into that column, right? And you want to capture the boundary conditions of that beam, you know, an individual element framing into that column, right? Multiple members, single node, this allows you to do that.
Yeah,
So,
I don't know why that was like just bothering me so much, or like, I was
Uh.
like, okay.
What does that last little bit say? Then what?
then we'll assemble.
Will, okay.
Will assemble. You have 3 weeks left to really be able to read my handwriting. Okay? 2 weeks left?
2.5.
Wow, okay, you guys are counting.
Yes.
I thought you
Three if
may have
count
wanted
finals.
like more time.
3 if you count finals.
3 if you count finals, which you'll need all of that week for sure.
No, we're not using
So it's critical, like we were just talking, Elias, right? There's a lot of conversations that go into how are we going to implement boundary conditions based on a given connection, okay? Right, that's why the extra credit in the homework is there, right? To think about how do we impose the right boundary conditions to mimic what's going on based on that connection type, okay? So it's critical to put thought into it. Why does it always keep going back to? Releases. It's easy to over-release a beam. Or that beam node intersection. Or interaction, I guess. In VA, there's kind of a shortcut to establish these releases. If you guys, I'm assuming most of you have seen it already. Well, when you click on a member, you can say, do you want it to be rigid, simple, right? Simple, rigid, or simple, connected. All that does is it's getting rid of the strong axis and weak axis bending at the ends. So you can have it, yes, Daniel?
Do you use the same releasing to capture this strong column, weak beam mechanism? What do you use to capture that mechanism?
That mechanism is captured based on the design of the moment frame, like on the AISC.
How does it work? In the lab was full.
Does that, like, you feel like that's an excuse?
The
That's
lab,
not an
I
excuse.
didn't give myself enough time to walk.
You never do.
I think I go pretty good.
Let me think about that. You completely messed up my train of thought.
I thought you guys would get through a lot without me here.
We did, actually. We did.
There we go.
We established the
More than
homework is
yesterday.
hard and you guys don't like it. See, are you okay with the homework?
I got it
I like
running.
the homework.
Yeah, see, look at that.
Running isn't
Mine
done.
run.
Yeah.
Will you publish how many changes you made?
That's what I
So
said.
yeah, I don't want
Give
to.
us something to
I don't
back it
want
up, or
to.
else we'll just stare at it and be like, well, is there something else I missed?
You gotta feel
Actually?
comfortable with it, man.
If it doesn't run, then you miss them.
Yeah.
Look at
Well,
that.
but even when it
Yeah.
does run, that doesn't mean it's
There's something.
right,
It's easier
accurate.
to run and have missed one.
I think there's somewhere around 20, okay? You guys beat me up
Yeah.
enough, right? Somewhere around 20, I think. I like started doing it and I was like, shit, I gotta stop. Cause you can just keep going. It was really easy to go the other way,
I
right?
see you had a lot of fun.
I did, I just like kept going. I got
It's
this
so
piece of
random.
paper
You just
here.
go like, oh, let's do this.
But it's
Let's
so
do
easy,
this.
right? It's so easy to do and you can make those mistakes along the way very easily. Back to you, Daniel. What were you asking me? Let's start.
Yeah, I was asking you about this strong column, weak
Yeah,
beam.
yeah.
Do we capture that through this?
You can capture that within the model, the way that, like, so the engineering building has a proprietary system called side plate. And so in order to make sure that there's strong column, weak beam, what they end up doing is they mash a bunch of huge steel plates on both sides of the columns and the beams. So you're basically cheeking it, putting two plates on both sides. And what that does is it makes the connection really, really stiff. And what's that do? That means that the beam framing into the beam to column intersection, right, and the column framing in are really, really strong and robust. They're stronger than anywhere else in the frame. And so then you pick the column and the beam size in such a way that the beam is like weaker than the column is, and then you establish that. And they do that based on testing. And so then that proprietary system is based on certain sizes of columns and beams. And you have to end up going through and checking the plastic moment capacity of the beam and making sure it's less than the column, so that it does do that. But what you can do in VA to maybe you are considering that behavior is the fact that, okay, now we have this massive block and we can't really ignore the fact that, like that it's not there, because in VA, right, we're going and we're putting nodes and we're looking at center line to center line, right? We're gonna have a node at the beam to column intersection. And when we're looking at that, here we go. When we're looking at that, can't just stop here, right? So we have this beam and this column framing in. What do they end up doing? Well, they end up putting this huge cheek plate assembly that goes across all of this. They bolt it all up, right, or weld it all up. So this whole system now becomes super strong. VA is looking at it like this, right? And so when VA is looking at it, it doesn't know that this plate's there unless you tell it that the plate's there. The way that they tell that the plate's there is they end up starting to put another beam out here, right? So they break this beam up. They say now we have two beams. This beam, right, and even this column sometimes depending on the model that they're doing. They're gonna make these really, they're gonna beef them up based on the fact that we're putting cheek plates on it. So this whole thing is gonna act as one unit. And now the beam span's shorter and you then get to model that, stuff like that.
Where do you release the beam at then?
So that if it's a moment frame, you wouldn't release it, right? Because it's completely fixed.
Not even outside that cheek plate.
Not even outside that cheek plate, right? It acts as though it's continuous, right? There is no hinge here. This isn't going to be able to rotate freely. It's connected rigidly because this beam in real life extends all the way to the column, But then we add all these chick plates to it that allow us to transfer shear and moment, right, across this intersection, the connection here. And so at this intersection, all you're doing is you're making a transition in stiffness, right, in size and strength. And so all you're doing is, okay, now I have, say, a W16 by 46, and then now here, they model it something else. Maybe it's a generic blob or some sort of shape.
Can you just use a rigid length for that?
You can, but
You gotta be careful.
side plate, yeah, because then you're saying it is infinitely stiff. Is that as accurate as you want it to be? Because then that's affecting the overall stiffness of the entire frame. And the overall stiffness in the entire frame, well, that affects your calculations on, well, what's the drift of this frame? Do I need to consider P delta, right? Is it meeting the wind load provisions, right? The displacement requirements for seismic, for wind, all of that stuff? And is that accurate to say that this is fixed? I don't know.
Would
For
they have to
side
publish-
plate, you send it to side
Yeah,
plate
okay.
and they change this model and they do this for you. And they do some proprietary thing, you just don't touch this anymore, right? It's like we've sent them RAM models and then they come back with a new RAM model based on their sizing of those members. Yes,
Sorry,
Madison?
I have
That's
a
okay.
different question.
That's all right.
How do you know if you wanna release out of plane or in plane?
Like whether I want to or,
Like if you had like a brace frame, I feel like in my head, you just always do the in plane one.
Yeah.
But there's also like the out of plane, the one that you can release too, right?
yep.
So how do you know which?
I mean, in a like 2D frame model where you would, if you just drew a frame in VA and that's it, and you added some sort of loads to this thing, right? And there was nothing else to your model, it's just this frame, 2D space, right, on one plane. Then bending in this direction, right, you have no forces in that direction, it's really not gonna affect what's going on here, right? You would really want to do some releases at each one of these nodes, potentially, right? Something like that, okay? And then in the out of plane direction, it's not going to affect it, right? Because this frame's not displacing in that direction. What you would want to do is if these are pins in real life, which in a brace frame, generally you assume they are, and you were having it in a larger frame model like the tower or Norm or something like that, then when you load it in the other direction, right, and maybe there's a diaphragm that connects this, right, there's a concrete on metal deck or something that's connecting all of this, then the stiffness for this thing bending this direction is going to affect what's going on in the overall performance of the model. And then you're gonna have to decide, right? You're gonna have to think about it and say, okay, should I release it? Should I not release it? I would typically release it, right? Same with like your joists, right, that are framing into girders or something like that. We release both directions, because when you look at a shear tab, and you have some beam attached to it, right? We're assuming it can do this, right, bend this way. But if you looked at it, you know, in and out of the page, there's not a lot of stiffness there either, right? You just have this little 3/8 plate, it's welded to some column. The ability for this beam to impose moment at that end is pretty limited also. But if you just had this gravity frame and you were looking at just one frame and maybe it was just a gravity frame, again, releasing the out of plane isn't gonna do anything if you're only looking at one plane, right?
So would it ever hurt to release both of them?
Not if it's going to behave that way.
Oh.
If you feel good about it behaving that way. If that's that, yeah, I mean, if that's how you're going to assume that connection behaves, then yeah, it should be okay.
So also with modeling those braces, you can't release all the members, because then that middle node can just spin, right?
Yeah, right.
Okay.
That's where you can over-release, right? Easy to over-release your beam node interaction, because if you go through in VA and you can easily go through and say, simple connection, right? Simple connection. All of a sudden when you do that, you've released all the ends of every member in the weak and strong axis bending. Well, pretty soon you're gonna have these nodes there that they can start spinning, right? Because they're released, nothing's holding that node there. Which is a very easy one to manipulate in a model, yes.
Do you want us to mess with the diaphragms at all? You didn't give us any information on diaphragms on that paper.
I'd say you can make that decision. It's up to you. Right? If you want to manipulate it, tell me why you manipulated it.
Oh.
If I didn't give you much information, it's kind of hard to make that decision. But if you
Yeah.
want to make that decision, you make that decision.
Okay.
It's yours. Yours to make. Impress me, Aaron. And I'm harder to impress than Damon, okay?
One more question.
Yes.
Do you ever release like a column to column connection, like going up a building?
Yeah, you could. I mean, like, sometimes we would have, like a girder that's spanning, like continuously spanning, and say it was,
Oh, yeah.
here we go. So say we had a building, it was 2 stories, and you decided that you wanted to run a beam across the entire second floor, right? And it was continuous, and you decided that you just wanted to bolt, say, the top flange of this column to the bottom of this beam. I would say that the stiffness of this is pretty limited, right? So you might want to release this, something like that.
What about if you have a column above, I think?
Yeah, that's kind of
What he was talking about.
But still, if you had a column above, just bolt it to the girder, you wouldn't really count on it resisting any stiffness.
Yeah, probably not. Probably not. I'd have to look at it and think about it a little bit. Like if it was a hanging column, like instead of holding this girder up, you decided you want an entire like big lobby area, they did, whoever did, and you're hanging this from up above, then again, I'd probably do a simple support there. If you had 2 of them doing something like this, I don't know why you wouldn't just run this continuous and then break the beam. And in that case, then I would say that it's rigidly supported. What ends up happening in VA is, if you guys remember, you guys are in steel design, right? When you have sway and non-sway frames, when VA goes to design this column, then it's going to figure out a K factor based on those charts, right? The stiffnesses of everything that's framing in all of your columns and beams. And so it affects your K value, whether this is a sway frame or a non-sway frame, depends, right? You go 0 to 1 or you go 0 to like infinity or something, or 10 to infinity, right? And so that's where that would play a role, is whether or not this goes through. And then in VA, the interesting part is we're not really going through the design module too much, just because you guys are at different levels, right, of design of members. But in VA, then it becomes important with respect to the K factor. Because VA, when it looks at a column, it looks at it from end to end, right? The 2 nodes that make it up. In VA, you can establish, right, brace points for Z-axis based on intersecting nodes. So even though you have a node here, VA might look at this column as one big tall column. You could split it, right? And then VA is going to start looking at it at this column to this column. That might not be as accurate as you want, right? You might want VA to look at it from a design perspective, expanding, you know, this entire length. But you could get that same behavior if you split it, made it continuous, right? Didn't release anything. So in stiffness eyes, these things are connected. They just happen to have different lengths, and then in VA, in the design module, it's going to look at those lengths differently. The design module is its own beast. Yeah.
Does VA account for leading column behavior? When you clicked it as direct box?
Yes, it does like the notional
Does it do-
loads and
Notional is
in-
columns, notional
Yeah,
is
but I'm talking like-
imperfections.
There's a method of like adding a whole nother bay to your model and like analyzing your leading columns that way.
I don't remember that. I don't remember
It's,
that.
it's,
Answers.
Yeah. So you're talking stability stuff?
It's just second order.
Yeah,
second
so
order
like
effects.
chapter C or whatever.
Yeah, and there's like one provision where you can like add a bay and then account for all like your leading column effect.
Mm.
The added P delta that you get from like having a bunch of gravity columns displacing a little bit as well, and you like add a bay to it.
Never done that before.
'Cause, yeah,
Thank you.
I've always done like the moment magnifier method,
Yeah,
right? B1, B2.
B1, B2, okay. Does VA do that when you check it?
No, it does. Yeah, it does the direct analysis method, which then takes into account, one, you have to reduce stiffness of your members,
direct
and
analysis does that.
yep, and then you have to, then it's taking on those notional loads,
Yep, okay.
which takes into account the fact that you have an inherent, like, misalignment, right? The like in the steel manual you guys have in the back, there's the specification for the erection or like the construction of steel buildings, and in there they give it tolerances for how straight a member needs to be, you know, both in fabrication but also in erection. So like L over 500, they allow you to then say, okay, this column, yeah, we assumed it's super straight in our model, but in reality, you know, things might not be right, the foundation might be off a little bit, so this column's now off by L over 500, so then they tell you to do notional ones. Okay. As I mentioned, it helps to show local coordinates and releases. If you guys haven't known already, circles are moments and blocks are forces. Okay. Super helpful. Very helpful for the homework, okay? Being able to look at a joint in the 3D view and be able to see what type of releases are on this member, right? Pretty easily. Okay, you can see whether or not you over-released the element, right? If you released everything that frame into this one node, then that node no longer has any support, and it's gonna spin, and that's an instability, okay?
You have like 2 sets of circles on it? Almost?
Yeah, it's a circle in every direction. Like if you zoom into the 3D view, right? This circle that we see right now is saying that the moment along the z-axis is released. If we had a moment that was released in the other direction, that circle would do this, right? That would be the torsional moment. That would be the moment about the x-axis. And then similarly, there'd be one more there, right? That does this. That would be about the y-axis. And then on top of that, then they start putting in just solid blocks. A block oriented along the axis is the force along the axis, right? A block that's oriented vertically is about along the vertical local axes. Okay, plates.
What do the blocks mean?
Blocks are that because you can release forces, right? You can release shear and axial forces in our member. And so if those are released in the model, then it'll show up as a little block, not a circle.
I've never seen
Yeah, like-
Well, because you never release that usually.
I was gonna say.
They're like very unique situations that you would release that,
Okay.
okay? Very, like when we connected the bridge into Norm, right? That bridge is supported vertically, but it's actually supported by the moment frames that are behind it. All the support's underneath that bridge that goes between the parking garage. Okay? Norm is just sitting there holding it up vertically. It can slide back and forth, it can slide in and out, okay? But at one point we integrated that model with the overall Norm model to make sure the reactions were what they should have been. And so maybe one case, right? But it's possible, right? You might have that be something you do, okay? Just wanted to show you what that was all about. Similar to members, plates are. Plates is. Again, some things to think about. Nodes are numbered at the local plate level. And it's based on how this plate was drawn. So if you started and everyone's drawn plates now, you click on the first node that you're gonna draw this plate on, that's node 1, right? Node 2, node 3, and then it'll generate node 4 for you. So that's how it's devised. Again, you can get rid of forces and moments, right? Those forces and moments follow the local axes. So if you look at these two plates, right, that kind of changes how the behavior's going to, like, how the stiffness of this plate reacts, right? Because it's all aligned with the x and y coordinates, right? With respect to these forces. And so, what's that?
When it auto meshes, is there any rhyme or reason to the numbering?
I don't know. I don't
You just
know.
gotta look and see.
Yep.
like, this.
Yeah, this one's really tough because, yeah, you can release. You'll be like, oh shit, I think that's node 1. You release it, and then hopefully you'll see it here, and then you'll say, okay, shit, I wanted this one, and you'll try node 3, and then that'll be that one. So then you come back and say, all right, it's node 2.
So, yeah, there's-
I don't think it. I don't think it will do that.
It's not like, looks like a clockwise.
No.
Counterclockwise or something.
Not that I'm aware of. All right, so it's not associated with node numbers. But to the creation of the plate.
When do you release your plates?
We're going to talk about that here in a little bit. We are. But before that, right, we have forces that we can release and moments in the local directions. And this is where the help file is very helpful because plates, I know none of you have taken plates and shells. Plates are very interesting elements, okay? In that the sign convention for the moments, right? The sign convention for moments is that a positive moment produces tensile stresses on the positive local, there's positive Z local coordinate face of the element as shown below, right? But then when we get into moments, right? The moment in the X direction or on the X face is really the moment on that coordinate face, right? Not in the, like the bending about that axis. That's the big difference here, right? So when you go up there and you release the moment, it's releasing the moment on that X face. It's not releasing the moment twisting about that axis, right? So that Y moment is really on the Y face. If you were to cut something, cut a plane perpendicular to that axis, that moment is going to be the Y moment. Z stays the same. It's the drilling degree of freedom.
Did you take plates and shells when you were here?
I did, yeah. Hopefully it's, what's that?
You thought it was valuable?
I thought it was cool. I don't know about valuable, but it was cool. Like, I mean, it was valuable actually, because it does give you a sense of how plates behave, like thin plate on, like simply supported on all four sides, and it has a uniform pressure on it. The corners actually want to pull up. And so when you're modeling something in BA, and then all of a sudden you get these really big shear forces and shear stresses at the corners, it's the fact that that plate is trying to pick itself up at the corners, right? Would not have known that without having plates and shells.
It's only like 2 credits though. So like, does it make sense for anyone to take it? We
Oh.
only need 31 credits.
It just doesn't
So
like,
then you just have to take another class.
so you're trying to get through this as quick as possible, right?
Well,
that's
That's
for
the
like,
intent.
it's like this class used to be 2 or whatever. but-
Yeah, yeah. So no one would have taken this class if I would have taught it with 2 credits? Is that what you're saying?
No, but having a B3 makes the lineup nicer.
Yeah, yeah, that's true. So you would rather take it if it were 3 credits?
It's
Yeah,
probably
'cause you
3
need-
credits worth of work, even though it's 2 credits, and so, yeah. worth
Yeah,
it
just
being
like-
3.
Where does that, like,
Credits
who
goes
decides
everything
on what the credit load is? Like, you
Right.
guys relating everything back to Damon's class? It's 3 credits?
No, it's the average, like, expected out-of-class hours for a certain amount of class time. It's like
Credits
30
has to
hours
do with
per
how
hour
much time you're
credit.
spending in class.
Yeah, yeah,
But like, that should also be reflective of how much time you spend out of class. If it's like-
yeah, yeah.
When I took geotech, it was a 3 credit class, and we were supposed to not have class one of the days of the week, and Kostrowski was like, we're gonna do class on Fridays, and everyone's gonna come in, and so it was like 4 credits of class hours in a 3 credit class.
Because you have a lab.
Yeah.
That's
but
where
it's
the
still
3
supposed
credits,
to
because
not
315
have
is the same thing.
But they changed it now.
No, it's
They-
just 2.
Yeah, they changed it to 2 classes.
Yes,
and a lab
but
because of
Geotech,
the
it didn't, they didn't.
I got like I always get the shit year.
Oh, man. Oh, man, poor Aaron.
And he
Poor
tried
Aaron.
to stick to that. He tried to do 2 classes, and if we had lab that week, he'd cancel like a class.
Well, could you look at it as like you got 4 credits worth of knowledge out of 3 credits worth of payment?
I would have taken plates and shells. They just don't offer it.
It was a deal. They don't offer it. Well, maybe I'll recommend it to Mike. I think it was an interesting class. I assume it probably was 2 credits then. I don't remember how many days a week it was, but
I
yes.
have a question for
Yeah.
Lynn Plates.
Yeah.
For the releases, it looks like you can just like release the nodes, but on the diagram, it looks like they're on the edges. Like how does that work, I guess?
What do you mean?
Where the buttons.
Like you can, it's like release FX1, FY1.
Yeah, so each
FX1.
one of those are the nodes. So like the releases I showed there
Yeah.
are the releases for the 4 noded plate. And so at each of those nodes.
So if you did it,
Because the node, like I just drew a 4 noded plate, right? And so all the plate nodes is what's happening at the nodes. And so all you can tell it is that at that node, am I going to be able to resist force or moment in the 3 directions?
so if you want to release like the MX in this diagram, like along that edge, you have to do both nodes.
You would, I mean, yeah, I mean, you would essentially, you would want to, if you wanted it along the entire line, you would have to do it on the 2 nodes that are common to that one boundary.
So those nodes though, are those, I would assume those are based on the local coordinate XY, like MX is about the x-axis.
Yeah,
for
so like do
nodes.
those X's line up with this X?
No, the
How
X,
do you-
yeah, the X's here are the local, like, bending moments here and forces here.
Or is there a button to say like I want to release MX on this plate or something?
Like, when you say MX as in,
As in like I want to do like release MX like it's shown in that picture, how would I?
then you would do it with these releases, right? Because these are MX, MY, and MZ. So in the local sense, when it's looking at the plate results, right? If I wanted to release the moment on the X face, so in this case, I think that's X, or this is Y pointing this direction, right? So if I wanted to allow this plate to bend in this direction, right, freely at, say, this boundary, I would get rid of MY at these 2 nodes, right, that make up that boundary.
So the bottom half of this page is for results that you're getting, not for when you're releasing, like you don't consider.
No, that's the same, that's what I'm saying, is
And then
that
what is-
this diagram is the same for the, like, this is the local behavior, because when you're releasing something, when VA gets the results, it's based on the initial boundary conditions you impose, right? So these are the same thing.
Yeah, he's saying that the sign convention is different, so you just have to use this sign convention.
Yeah, what I'm
MX
saying, yeah.
is not moment about the X that you would think.
And what about?
So
Right, when you're looking at beams,
Use
when you
this
release
for
MZs,
these.
it's the rotation of the Z axis, which is acting.
So if I wanna release MX about like the 4th node, it's not about the
X-axis.
x-axis,
It's
it's about the
X
direction,
face.
X face, even if it's not on, yeah, okay,
You know what I'm saying?
sure.
Heavy shit, right? This'll screw you up. Screwed me up for like first couple of years working because I was like, I printed this off and it was on my wall in my office because I can't remember who brought it to my attention, but I dug into this and I was like, oh shit, because validation wise, you'd start looking at things, you'd say, all right, what's MX, right? And it's perpendicular to the direction that you would expect it to be. So if I like had a slab that I was designing that spanned between 2 joists, right? I'd assume that the dominant direction was in the short direction. I'd be showing MY and I'd be like, what the fuck? It's like 0, right? And then the other one, and so then you start understanding that the sign convention is different and you just have to keep track of that. Risa?
I haven't modeled plates recently.
Okay. It's a good out. It's a good out. Simon.
What about MXY?
MXY is
That
the
should release-
moment on the X face in the Y direction
Well,
and
how-
vice versa.
Should you release that?
You can't release that.
Okay.
No.
So MX1 is like the moment on the X face, but 1 is like the strong.
No, 1 is the node at which you're releasing it. So nodes 1
X
through
face in the Y
4.
direction seems like the same thing as MX.
I think is it the Y
No,
face?
because it's on that, like, it's back to plates and shells class. It's the, like, this torsional moment. And that's why when you have a plate that's uniformly or like simply supported on all 4 sides and has a uniform load on it, that's why the ends pick up, is because you get this kind of torquing moment on the edges of that member that work together at the corner and they end up trying to spike the corner.
Why would you release?
What's that?
Releases.
Yeah, that was my next.
Not there yet, dude. Jesus. God, you guys won't let me move forward. All right, here we are. Plate releases. When the hell do I do this? Makes no sense, right? Plate releases. My goal was to get through all of the notes that I've posted out there by the end of the week. I don't think that's gonna happen.
Um,
But that's okay.
conversation.
Is this valuable, learning about 2 credits versus 3 credits and
Not
geotech?
that part, but the talk.
Plates and shells, right?
When is Loveland coming in?
Oh, so now you don't even wanna hear me talk anymore? Damn. 2 weeks from today. He's gonna come in on the Wednesday before finals. And Adam, I'm hoping to get to come in that Friday before finals.
Also, are we still doing like a structures tour on Friday?
That is still up in the air. Sam was, I don't know, I guess maybe
We
not.
just said wait for another email.
Yeah.
Even though it's in 2 weeks.
I know, I tried. I tried. Any ideas? I guess I drew a couple, no, it's okay. I drew a couple,
Some wells.
schematics here. Any ideas of where you might wanna release a plate? Aaron, come on, you model shit all the time. Where would you release a plate? Have you ever released a plate?
I don't really
Plate
play.
or-
Wow. Woo. Man. Any ideas? None? Come on. Structural engineering, what kind of big plate elements do we have? It was on the first exam.
What happens if you have an overhang?
What's that?
Is it an overhang?
Overhang?
Footing?
What were some of the things you put on the exam? A shear wall, out of plane. Thank you, Greg. Man. Next bonus word's gonna be Greg. Shear walls. Right? Obviously, again, as we talked about, if you model something in 2D, you say have a multifamily or a hotel or something like that, and maybe you decide to put concrete shear walls on the end of it, right? Not very common, but say you do, okay? You probably won't design the entire building in one model. You'll look at all these flexible diaphragms, you'll distribute all the loads as you need to that, big concrete wall, right? And you'll put maybe that wall in BA, maybe fix the bottom, right? And you put all these loads at the different levels. Right? In this case, you probably don't really care about releasing the out of plane direction, right? But the second you take this guy and you put it inside a very large model that is moving in the 2 directions, right? Then at this point, you don't really want the contribution of this wall bending out of plane, which it can be stiff enough that it's going to be taking load, right? And a lot of times we don't design these walls to take that load, right? And so we can get rid of that out of plane bending capability at the bottom of this wall, right? Which allows us to really design this wall as truly a shear wall, right? So that would be a case you might want to deal with. Some plate connections. Okay, that's one here. Or if you were building a built-up member, or say you had some weird shear connection, right, where you put 2 plates next to each other, and you decide to run a fillet weld along one side. Obviously, the resistance for this plate in bending is going to be very limited, right? So I wouldn't want to design this billet for bending it over, so I would release the moment capability of this plate at this connection to make sure that we don't have any moment, and the load that it would carry goes somewhere else, right? It's got to be carried somewhere. If we say that it's 0 moment there, we're going to design it to go somewhere else, right? Some wall intersections. So if we're looking in plan view, right, we have this box, maybe it was a tank, we'll talk about that here in a second. Okay, so this is plan view. VA looks at it as just these little plate elements, right, that are standing vertical between nodes and say the corners. Looks like something like that in section. Right. You might design this if it had some sort of support structure on the top. Right? A foundation wall for a house is a good example of this, right? Where you'd have a floor system that essentially infills between all of your foundation walls. So now you have this nice diaphragm that's sitting up there, right? And so when the soil's pushing on this wall, you might assume that it's pinned at the top, right? Well, if it's pinned at the top, you might want to release that at the top if you have other things connected to this plate, right? At the bottom, you might assume that instead of being fixed pinned, it's really pinned. Maybe you have a slab that sits at the bottom of this foundation, right? Concrete slab in a basement. And you might say, okay, well, I want this thing to do this. And I want it to be able to rotate, okay? I'm gonna just have one layer of rebar in this thing. Its moment capacity is gonna be pretty shit. It's gonna crack, it's gonna rotate. I don't really want to design this for the moment, so I'm going to release the moment of this plate attached to this footing, okay?
That plate connection on the left, I would think to just pin the nodes in that direction instead of releasing. It's a
Well, if
plate.
you had a plate that was running underneath it, right?
Right, you couldn't pin that, right.
You couldn't pin that,
True, yeah, okay.
right? So it's that interconnection of the elements that we're worried about. So some wall intersections might be a place where you would want to get rid of it. It's anywhere that you feel like, Jerry Stevens put it pretty well once, and put everything well, honestly. Did anybody have Jerry Stevens? No? Just before you guys, really? Anyway, he did plates and shells, one of the professors here, and he basically said, like, cause I was like, holy shit, like what if we do this wrong, right? Or like load might go somewhere else. Well, as much as we may think that our structure is going to behave like in a very indeterminate fashion, right? We have all these partition walls, we've talked about that, whether you design them to be contributing or not, right? Our structures are really going to behave in such a way that we are designing them, right? If we put a zero moment, right, or sorry, we put a release here, and we don't allow a moment to be passed here, that load's gonna go somewhere else, right? And we're gonna design that element to carry the load that would be here if it were fixed, right? And so overall, our building is really gonna behave in such a way that, and really follow the design that we impose upon it, right? So if we design something to carry force, it's going to carry force, right? If it doesn't carry force, we design it not to carry force, it probably won't carry force, right? But overall, the big picture here is that we need to provide a load path. There needs to be some way of getting it from the load source down to the resisting element, okay? Because I mean, it's a guess, right? It's a big educated guess. Oh my God, all right. So what'd you get out of me today? I messed up about 20 things on that homework assignment, okay? Somewhere around there, I couldn't tell you that,
So
because
if
like
you
when
get
I
at
was
least
doing it, like
20, that's
I could
good
do the
enough.
same thing on multiple members, right? Is that doing one thing or is that doing like 3 things, right? The number's kind of tough, like don't just hit 20 and be like, all right, I'm done.
Shit,
Yeah.
did you keep track? Did you keep track of it? Like,
I
you
did.
want a little, I have a little list,
I did keep track.
and then you want a model description as well.
I want a list, and if you were here at the beginning of class, Amanda had a great question about whether or not you need to describe why you changed that. And yes, you need to describe why you changed those things too. So I just expect, it doesn't need to be a paragraph, just be like, this node was 2 feet off, I moved it,
Is
right?
it, yes,
To align with
and
the
let's
model.
just say, it doesn't match the layout that you gave us,
Yes,
or
yeah,
the-
that, it can be as simple as that, but I wanna know why you got rid of it, why you moved it, why you changed the load on it, why you changed the releases, like, why did you do that? Okay, a lot of them could be, it doesn't match the layout, it doesn't match the behavior of the shear tab, it doesn't match this, it doesn't match that. Okay?
Version.